G'day there. You're watching the Aussie BIM Guru, and today we're covering part 9 of my feasibility series in Revit and Dynamo, and we're covering quite an interesting topic today, which is sun hour analysis. I will explain what this actually is for those that aren't aware of the study. So we've looked at setting up our feasibility mass and our site, and we've also done some surface analysis and some view analysis of our building as well. And then we'll put it into Power BI at the end. So we've set up this sensor grid on our building in part 7, which essentially allows us to receive data to the surface of our building quite early before we've even done like planned arrangements of our building. So we can form rough analyses of our massing and decide how well it's performing from an environmental perspective. So in the last part, in part 8, we did a view analysis using these sensors to see if lines between these sensors and the landmark could actually reach the destination by flashing it against our site geometry, essentially. But now we're going to do solar analysis instead, so seeing how many hours out of a time range the building will be able to receive sun. And the reason we're doing this, for a bit of context, is that in Sydney, we're required to follow a standard called CEP 65. And part of that is actually making sure that apartments you design receive at least 2 hours of direct sunlight between 9 and 3 a.m. and 3 p.m. in midwinter. And it also has to be in increments of 15 minutes as well, at the very least. And also a maximum of your apartments of 15% are allowed to receive 0 hours. So it's quite a tight requirement in terms of proving that your building form and location of your living spaces is compliant. It's important to note that the script today is going to work at a very high level. It's only going to work in hourly increments, so it's not accurate enough for CEP 65. In the next part, I will show you how you can refine the script in order to make it much closer to the requirements, but it will take longer to run as a result. So as I said, CEP 65 requires 15 minutes of continuous exposure at the minimum. So we'll refine it to get closer to this, but it's not impossible, but it's very hard to build a script in Dynamo that is fast enough to be able to give you such a detailed analysis. I'd say if you're doing a proper full detailed analysis, Grasshopper and Rhino are probably a better version of the script to build in, so I'd probably actually recommend looking into that a bit more. There's a really great guide at a website called Parametric Monkey, which I highly recommend checking out. It's actually been around for quite a while, this guide, but upon this website there's almost like a blog which covers a workflow written all the way back in 2015, so you know, this guy was ahead of the time in some regards, and he goes through a detailed analysis where you can actually get very accurate results. You can actually check exactly how much sunlight in square meters you're getting on the floor of your room. So I highly recommend checking that out. But today we're going to focus on, I guess, a high-level version in Dynamo that works directly in Revit. So we've actually modeled a little bit more of our site now. So we've modeled the whole northern context as generic models. Took about maybe 20 minutes. So probably not a big issue. It doesn't take too long, just so the data is easier for Dynamo to handle. And we're basically going to cast a whole bunch of sun vectors from these sensors and see how many of them clash with our site. And then we're going to tally our results, and we're going to use filters to represent how many hours are being received by each sensor to give us a rough idea of where the best locations for living space placement are in this particular mass arrangement. And we can also tally the results because our sensors are going to receive data as well, so we can also schedule them, so I'll show you how to do that too. So today we're going to be using weather files. There's a website called Energy Plus where you need to download what's called an EPW file. I assume that's an Energy Plus weather file for the format name, but essentially you can search for any city that they have data on, and they do have a majority of the major cities in the world, and that will give you things such as sun vectors, which we're using today. And we're going to be processing that using a package called Ladybug, which is available in the package manager in Dynamo, and it gives you a lot of nodes that relate to weather, site data, so this is perfect for sun vectors. And we're going to be using some custom nodes from Ladybug in order to deal with building up that sun study, and also the if node from Zebra. So feel free to get those. And I'm using, I think, Ladybug version 0.2.1, but I believe that these nodes should behave in most versions of Ladybug the same way. So I think we'll use version 2.0.3 in this demonstration of Dynamo today. However, I think you'll need at the very least version 2.0 to run a script like this. I think some of these custom packages don't behave the same way in version 1, for example. So I highly recommend using version 2, and ideally 2.0.3. But anyway, brace yourself. It's going to be a little bit bumpy. It's a complex script, so I will probably take a little while to put this script together, and the results will take a little while to process, but I think it's a highly valuable scripting process in order to encourage other people to explore solar analysis using computational software. So without further ado, let's get started. So I'm just going to jump into my site in Revit. So as I said, I've actually added quite a lot of elements to my site. So I'm just going to hide my southern context, and what I've done is I've actually expanded my central context of my site, and then I've just modeled up the eastern and the western portions as well. And the way I assessed how much of the site I needed to model was more or less anything that had the potential to block the sun to any of my sensors on my building. I probably didn't need to model every single one of these buildings, but I did want to also have like a relatively whole site context for 3D axonometrics in the feasibility study as well. I think it's highly worthwhile just doing this if you have time, because it will make it a lot easier than working with the AutoCAD site, which currently I've hidden in this particular view, but it is still there at the moment, but I basically just modeled over the top of it. Okay, so we're just going to get started. So the first thing we need to do, I'm just going to turn on my detectors, and I'll explain some of the setup that I've set up in the background here. But at the moment, our sensor family, I've actually added a new parameter to it. So if I go into its type properties, I've added a new shared parameter under analysis results. Where is it? Actually, I haven't added it yet. Okay, I still need to add it. Good. So I'll take this step now. So I need to add a new parameter to this, and I've set up a shared parameter in this case, and I've set up a parameter called data sun hours 1, and essentially this is just a number field which is going to represent how many hours of sun that sensor receives. It's a number parameter, so you'll need to make sure yours is also a number parameter. So we're going to add that as an instance parameter. Usually I put mine under analysis results in the family, just because it really does relate to an analysis result. And by default, I set it to 0. Okay, so okay that, and I'll save. You can save your family if you want. Doesn't really matter if you don't, as long as the project version has that parameter. And essentially after that point, every sensor in your model should now contain that parameter. We're going to be scheduling this parameter as well, so we'll also need to add it to our project parameters as well, so that we're allowed to schedule it. So under project parameters, you'll also need to add it in the same way here, which means that technically every generic model in your project will have this parameter, but the only ones that really matter are the detectors in this case, because they're the only ones we're processing that data from. I've also set up some filters as well, because we need that project parameter to be able to filter as well, actually. And I've just set up a bunch of parameters that basically say the sun hours, do they equal 0, do they equal 1, do they equal 2, 3, 4, 5, 6, 7. So basically these will apply an override on a filter to sensors. So at the moment I've set up just a range of colors for each of those filters. So you can see I just go from blue through to green through to yellow, just to represent how many hours we receive. So if I change one of these sun hours on one of these sensors to say, let's say we get 6 hours of sun, you can see it's much more bright. And obviously if I set one to say 7, which is the maximum, obviously it's very bright. But be careful with this shared parameter on other families. So for example, this one here, I don't see if I told this it had 1 hour of sun, you can see it overrides this element as well. You could refine your filter to only apply to sensors if you wanted to. Okay, but now we're actually going to work with Dynamo, so we're going to start building our script. Okay, so the first place we'll begin with is with Ladybug. So we're going to build our sun vectors. So the first thing we need to do is we need to import an EPW file. And actually we won't do that. We'll import location from an EPW file. So we need to get a file path, and we need to link to our weather file. So I'll just link to my Sydney weather file, and that will give us a location and an error report if something doesn't work. From there, we need to actually build our sun path under the visualize section of Ladybug, and all you need to do here is feed in your location. If for some reason you're not working at true north, you can set a correction between 0 and 360 degrees here. I think it works in the counterclockwise direction, so feel free to experiment with that if you're not working to true north in Revit. And keep in mind that Dynamo North and True North are not the same. So if you've already rotated your True North, it may not necessarily work unless you also rotate the results here as well. Okay, so we're going to build an hour of the year range now. So we need to calculate hours of year. So we're going to feed our hours of year into SunPath, but we need to actually set up a range. So we're going to get some integer sliders in order to set our ranges. Okay, so the first one is going to be our month, which obviously is between 1 and 12, and by default I'll just set that to June, because that's when we undertake our SEP65 analysis typically. And I'll just make that a single slider. For day, likewise, we will work between 1 and 31, and I will set myself to the 22nd, because that is usually the most common day that we test as well in June. From there, we need to pick our hours. So our hours, we actually need to build a range. So we're going to build one using the syntax of start and end with a step of 1. So basically S and E are variables in this case. For minutes, we won't set this at the moment because by default it is 0. But we will come back in our next part and refine this section of our script in order to measure increments at 15 minutes instead of at an hour, because we're measuring on the hour basically using this script. So for hour, obviously we go between 1 and 23, and we're going to measure between 9 AM and 3 PM. Make sure to use 24-hour time. Okay, and that should give us data at that point. I'm just going to save my script because I haven't saved it yet. Okay, so at that point we should be able to get a whole bunch of data about our site. But what I just want to check is our vectors. So I'm just going to put a watch node in here just to show you what comes out. And also I'll put in a date time watch as well, so you can see the date times that it's generating. It generates a whole bunch of data. We're just going to run and see what we get. So we should get a range of times. You can see that it actually does visualize the SunPath as well, which is pretty cool, but it sort of gets in the way in Dynamo, so I tend to turn off the preview for SunPath. Okay, so you can see now we have 7 vectors. These represent the direction of the sun facing towards us. So we're going to need to reverse this in order to move lines away from our points to clash. So we're going to reverse these vectors using the reverse vector node, so that they face the other way. So we're pointing towards the sun now. You can see there, these are our date times that are being generated. So that's what these vectors correspond to. Okay, so we're going to reverse those vectors. We may flatten our list first as well, because I believe they come out at a level. Oh, okay, no, it looks like they're okay. I might just flatten it anyway, because I believe that we'll be setting a cross product on here later on. So probably, yeah, we need to cross product our date time. That's right, because we're going to be mixing minutes into here later on as well. So we're going to cross product that. But so then we're going to flatten our list and generate our vectors so that our cross product will have its levels removed. So that should work at that point. I don't think the cross product will matter at this point because we're only running one range of time, but we will need it later on. Okay, so our destination node at that point is line by start point, end point. And this, actually we need line, that one doesn't work, so by start point direction length, that's right. So this is our direction, essentially. What we need now is our start points and our length. So our length is quite easy. That's just how far away do you want the lines that are going to clash with our site to reach. Usually you want this to be a pretty big number. I usually set my range, I think between, I think it's 500,000 and 2 million, because this is in millimeters at the moment. You could set up unit conversion if you wanted to. And I'll just set that to 1 million at the moment. And you'll see what this does in a sec. But essentially that's how far our vectors will reach. Okay, so we're going to go back now and we're going to get our detector families. So we're going to get our family type node. And the reason we're doing family types is because you'll remember that we set up a type to deal with landmarks and we made that a separate type. So we want to only pick the type that we're using to detect. So we don't want to use our viewpoint type, just our typical type. Okay, so we're going to do our family instance by family type. And that should give us all the instances of our family type. So from a family type, give us all the placed instances. And we're going to have quite a lot of them. You recall that we had, I think, about 1561 sensors. So quite a lot of data. And what we're going to do is we're going to manage out a few sensors in our study, because you'll recall that we have a podium zone and a tower zone. and our podium is actually commercial, so our requirements aren't going to apply to this area. Whilst it is possible to test the solar performance of this area, just to prove to clients how much sunlight their office may receive, or potential tenants, we're only really checking our SEP 65 requirements for our apartments in this study. So we need to filter them out, and the way we're going to do that is to use some filters. So first we're going to just obtain all the sensors that belong to option 1B in this parameter, and then we're going to find all the sensors that contain the word tower in comment 2. And that way we won't get any of our podium sensors. The reason we want to do that is the more you can refine your study, the faster it will go, because we're going to be checking a lot of things, so it's going to be a slow script to run. So we're going to get some parameter values of these sensors in order to filter them down. So we're going to get the parameter value first of the parameter for comment 1. In my case, I've called that ABG data comment 1. So we're going to get that value, and you'll see that we should get a list of 1561 results. In this case, they're probably all called option 1B, but you can imagine if I've got 5 different studies set up, we don't want to go and get all the sensors in the whole model. We just want to get the ones that relate to that particular study. Okay, so we're going to use a string contains node in order to filter. So we're going to check if that particular string contains a substring, and in this case, we're just going to say we're looking for the whole string, option 1B. And we'll just add a boolean to say to not remove case, or to not ignore case, sorry. So we'll take that out. Okay, and then we're going to use a filter by boolean mask. For those that have watched my videos for a while, you'll know that this is probably my favorite Dynamo node. It's really great for data filtering. And we should be left with a list of only the ones that relate to our study. But in this case, this will be still all 1561, but the out list would be anything that doesn't contain that particular piece of data. Okay, so we're just going to move this away again, because now we need to filter this data again. So we're going to take this bunch of nodes that we've just used, and we're going to create a new set of them, because we essentially want to filter again. So we're going to take the result of the first filter, and we're going to filter a second time. And this time we're filtering comment 2, and we'll filter for the word tower. So we'll make sure that's capitalized. And then we're going to take another filter by boolean mask, and we're going to mask the in of this list. And again, we'll just move that out of the way. So now we will expect our data to split. So all our podium sensors will probably be going into our out list now. So you'll see that we'll actually have a bunch of sensors we're managing out now, 572 of them. So we've reduced the intensity of our study by a factor of a third. So this will at least make our study a little bit faster to conduct, and it means that we're refining our results. Okay, so at this point now we need to actually get the location of these sensors. Okay, what's that? Element location. It'd be nice if sometimes these things had a little bit more descriptive names. You sort of just get used to seeing where each one is. Get location, get existing elements location. Okay, so we're going to get the location of all those sensors. Before I do that, I'm just going to set my geometry scaling to extra large, just in case, because sometimes Dynamo needs to be told it's dealing with a large model, because we will be grabbing our site after this. Okay, so we'll just run this, and we should get a bunch of points in Dynamo that represent all our sensors. And there they are, in all their beauty. So that's our tower, essentially, at that point. Okay, so from there, we're just going to add a little node here so that we can limit how many sensors we're dealing with. I'm going to use a node called take every nth item. And we're just going to reduce the number of sensors we're dealing with for the demonstration. And then at the end, I'll show you a full demonstration, because it will take a little while to run this script with a lot of sensors. So we're going to take that list of locations. Actually, we're going to take the in, and we're going to add this in the way. So from that list of sensors, we're going to intervene with this node, and we're just going to take every 100th sensor, and we'll start at the first item. So now we'll only get a smaller sample. So we're only going to just get a small range of sensors distributed around our building. We could grab more, but I think this is enough to show how the script works. Okay, but then at the end, what we'll do is we'll just come and reconnect this across here to stop the nth item from reducing the number of sensors. This is a way you could control the sample size as well, if you have too many sensors. But I always recommend setting up the number of sensors you're going to need to correlate to your results. Because there's various aspects of the sensors that relate to how many are there, such as the count and the area per sensor that we've already established in their parameters. Okay, so at this point we need to actually take these locations and we need to list map this function to generate lines from these points for each vector. So we're going to take all the locations and we're going to list map this function. So basically the way list map is going to work here is the point of the sensor will generate a vector, and we're going to set our lacing to longest as well in this function so that it generates as many vectors as this list is giving it. So it's going to generate a range of vectors for each of these to this distance that we've nominated here. So I'm just going to zoom out a little bit and we'll just run the script to this point. And there you go, you can see that now all our sensors are generating sun vectors, or sun vectors as lines, and we can use these to clash against our site. So you can see really easily how this is working. So at that point we actually need to get our site, because we're going to feed this into a geometry intersection node. So we're going to geometry does intersect. And essentially if this line does not intersect with our site, it represents a successful sun vector. So we're going to be taking our geometry and we're going to be connecting that to our site geometry. So I'm just going to freeze this node temporarily. And we're going to go and get our site's geometry. So we need to actually get a select model elements node at this point. And we're going to select multiple pieces of our site. So we need to minimize Dynamo so we can see our Revit model. You can see our results visualized in Dynamo there. So you can see that they get past our building. So we're going to have a successful clash with our site. Okay, so I'm just going to turn off exclude options so that I can pick my building mass and then my portions of my site. And what I want to do is just temporarily isolate those elements. That way I can really easily marquee them with my select model elements node. So I'll marquee them and you can see now we have those 4 elements. Okay, so I'll just reset temporary hide isolate and I'll go back in Dynamo. Okay, so from that we need to get the elements geometry. Should be around here, this one here. Okay, so as soon as we run this, we'll expect to see our site in Dynamo. So I'll run this and show you what we get. We should get a set of solids. So that's our site, essentially. And that's why I recommend modeling it in Revit, because it's much faster. And you'll see that it includes the building mass as well, because we want to see where these actually clip the building itself. Okay, so you can see we've got a set of solids. We actually have 134 solids. So that's far too many. And these are all set in sublists depending on which thing we selected. So each part of the site knows how many solids it contains. So we're going to flatten this entirely just so that there are a whole bunch of solids. And we're going to turn off the preview for element geometry at that point. So we'll flatten this, which will just give us a list of 134 solids. We're going to turn off the preview for that as well. And what we're going to do is just do a solid by union. And this will turn all these solids into one. So we'll feed in all those solids, and our result is just going to be a single solid that is every building that we've picked. So this is our collision detection method, basically. We're going to feed this into our geometry does intersect node. Okay, so at that point, I'll run the geometry does intersect node, because we've only got a few sensors, so it won't take too long. So I will run that and show you what we get. So from that, we'll get a list of trues and falses. So each sublist represents each sensor. So essentially, the sublist at index 0 represents the sensor over here at index 0 in our take every nth item. So that is the sensor's results. So this is how we can figure out how many sun hours the sensor's received. Every result of false represents a successful sun hour, and every result of true represents an unsuccessful sun hour that collided with our site geometry. So we're going to feed a logic if node in at this point from Zebra, the Zebra package, logic if. And we're going to feed these booleans in. So basically, if it's true, we had if it has collided and given a true, it's 0 hours of successful sunlight. And if it's false, it means that it worked, which means we have 1 successful hour. So we're going to feed that in, and essentially logic if will just turn this list into a whole bunch of zeros and ones instead of trues and falses. So you'll see how that correlates between our original results. And what we have to do now is just sum the contents of each of these sublists. So I'll just sum those lists, and each of these lists will now become a number. And this represents how many successful sun hours that sensor has received as a result. So pretty exciting. We've got to our destination. So all we need to do now is just set the parameter of sun hours. So set parameter value by name. Set parameter by name. We're going to feed that in as our value. Our elements are going to be back here as our take every nth item, which will feed back into our main sensor results. And our parameter name is going to be that sun hour parameter that we set up. So in my case, it's called ABG data sun hours 1. And that's our results. So I'll just quickly run this script. I'll probably just turn off these lines because they're quite distracting in Dynamo. So we just need to stop the preview if that's that list map. And we can also just stop previewing our element location as well. Okay, so in Dynamo, now if I run this script, we should expect to see some of our sensors get picked up by the filter. And there they are. So you can see one's here. So this sensor now it receives, I think, 4 hours that color represents. But there'll be other ones too that have more sun. So you expect the ones on the front face of the building will receive quite a lot of sun. So you can see that one there receives 7 full hours of sun. So it's really easy to visualize just how our building is performing. We can actually go and do the entire building, which I will do now. It will take a little while, so I might cut out this part. I estimate it takes usually about maybe 2 or 3 minutes at least to run a sample of this size. So what you'll need to do to run the study properly is we'll need to take our every nth item node, and we'll feed in our in node back to element location. And then we need to also feed our in node into the element that we set the parameter of. And then we just move our take every nth item off to the side. And you can just keep it there as a tool for later if you need it when you're testing the script. Okay, so at this point I'm just going to run the script, and I'll probably cut ahead to when it actually finishes. So I'll just move this. What I might do is just hide my site as well, so you can really see what happens to the building. Okay, so we're going to press the magic button, and we're going to wait. Cool, so we've just finished running the script. It took about 3 or 4 minutes to run that. So a little bit slow, but that's, I guess, the drawback of using Dynamo and Revit's geometry engine. But as you can see, we can really clearly see how many hours certain portions of our building are receiving. And we can sort of start to assess why this is happening. So you can see that obviously this building is leaving quite a strong footprint in the middle of this face, which is great. But even better than that, let's actually go and schedule our results to get more informed feedback of what's happening. So we'll make a new generic model schedule. I'll just minimize Dynamo. Okay, so we need to make a new schedule under schedules and quantities, generic models, and what we'll do is we'll add our sun hours. And you'll recall that we made a count parameter back in the last part, 2 parts ago in our sensor family. So we're going to use this instead of the actual inbuilt count parameter, because this lets us use this in formulas. So we're going to add that one as well, and we'll add comment 1 and comment 2, and probably area 2 as well, which is the overall controlled area of that sensor. So we're going to filter by the comment 2. We'll do comment 1 first actually. So we'll do comment 1 equals option 1b, and comment 2 needs to contain the word tower. So at that point we'll just OK, and what we get is a big data dump of all our sensors and all their results. So we can see how many sun hours they received. It's one sensor. We can hide these 2 parameters, so we'll do that. So we're going to go to formatting, and we're just going to hide comment 1 and comment 2, and we're going to sort our schedule. We'll probably just sort by sun hours, and we'll de-itemize our schedule. So now we can see how many sun hours overall we received. You can see none of them received 6. But what we're going to do now is we're going to make our count to calculate totals. So we're going to calculate totals for count to, okay, that. And now you can see instead, we can see how many sensors got these particular results. Likewise, we can do the same for area 2. We can sum how much area overall this represents by calculating the total of that as well. So now we can see the rough approximated surface area of these sun hours as they're relative to our mass. What we need to do now is add a calculated field as well to find out what percentage these hours represent. So we're going to make a calculated field, and we're just going to call that percent. And we're going to make it a percentage, and we're going to do the count to of grand total. So out of all the sensors, what percentage does each represent? And now we can see that we have 39% of our sensors have 0 sun hours. So we can see in this case that our south face is quite problematic because there's no sun hours on the entire face. So we are going to have to be very careful of where we place our living spaces in our building. We need to avoid our south face, which is pretty logical. But we can also see other things such as the fact that we're only receiving 10% of our sensors are receiving seven or more hours in the range, which isn't that many actually. So we're getting quite heavily obstructed by our site in most cases. What you can also do is sort and group your schedule based on the face that it appears on. So you recall that comment 2 is actually east, west, north, and south tower, depending on which face we're on. So if we sort by that instead, and then by sun hours, and we make our comment 2 a header with a footer that represents the totals, and a blank line, and then a grand total with totals only, we'll get a schedule that looks a little bit more like this. So now we can look at each face in more detail. So now we can really see just how poorly our south face is performing because the majority of our 0 hour sensors are upon this face. You can also see as well that our north face is performing not that great either. There's 9% of the face is receiving no sunlight, 10% is receiving full sunlight. But you can see our west and our east faces for the most part are performing quite well. We're getting 2 or 3 hours or 3 or 4 hours on these faces. So we know that we need to focus on these 2 faces for our living areas wherever possible. So this helps us make more informed assumptions about our design moving forward. So that's pretty much all for today, but that's, I guess, how you can do a sun hour analysis. In the next part, we're actually going to be refining that quite a lot. So in the next part, we'll refine it to work with the 15-minute intervals. It's quite a lot more of a complicated process because we have to process our results quite heavily. So that's why I've made it its own part. So thanks for watching today. Hopefully that gives you a new tool you can work with and gives you a more complicated script that you can play with and probably improve and innovate upon. It's one that I've just developed myself, so there's probably lots of other ways to tackle the problem. If you've got any feedback, feel free to leave it down below. And hopefully I'll see you in the next video. Thanks. Take care. Bye.